A very good morning to the audience. Let me first thank the organizers, especially Professor Sergey Flaha, for the kind invitation. It's a pity I cannot come to the conference physically, but it's still good to be connected online. So I hope you can see my screen clearly. So my talk is about the non-equilibrium topological matter and its possible applications in quantum computation. So I'm from the Department of Physics and the Center of Quantum Technologies at the National University of Singapore. So before we touch upon the details, let me first acknowledge my collaborators. On the theory side, it's Professor Zhou Longwen, who was my former student and postdoc, and Dr. Zhu Weiwei, also my postdoc at NUS, and Professor Radhika Bomantara, my former PhD student and now a professor at Saudi Arabia. I also have experimental collaborators from Professor Sifai Zhang from USTC China, Professor Du Jiangfeng, USTC China, and Professor Zhang Baile from NTU, Singapore. So the funding comes from the Singapore National Research Foundation Investigatorship Award and Singapore's Ministry of Education Tier 3 grant. So this is the outline of today's talk. So it looks like there are a lot, but I think the details are not that important. What's really important is the ideas behind some details I'm going to present. And I think the key message I'm trying to share today is that by driving, especially periodic driving a quantum system, you can generate many non-trivial topological phases of matter. And those non-trivial topological phases of matter can be quite useful in either basic research or in possible design of new quantum computation schemes. And I think, so with that spirit, I think what's most important is the introduction, motivation, background of this research avenue, and what I can conclude from those activities. So this story, in my point of view, can go back all the way about 14 years back from some studies from my own group at NUS. So back in 2008, 2009, since this is a dynamic days conference, right? The key key item on the study is dynamics, right? So we played with the dynamical systems. In those cases, you see one-dimensional quantum systems. And by engineering different time dependence of Hamiltonian, we discover that you can actually generate this kind of fractal or multifractal quasi-energy spectrum by periodically driving the system, or by some periodic engineering of the periodic driving of the system. So back then, of course, the recognition of the importance of topological matter is not as widely accepted as today. So when we look at this, right, so we realize, oh, this kind of multifractal spectrum, now, even though it's in the so-called quasi-energy, not energy itself, I'm going to explain what quasi-energy is next, looks exact same as the paradigm spectrum of so-called Hofstadter butterfly in the integer quantum Hall effect studies. Yeah, literally you can compare those two spectrum. I wouldn't see, you can actually see any difference from the screen. So that's a good indication that you can actually use time dependence, engineer the time dependence of simple Hamiltonian system to generate topologically rich spectrum. Okay, so that's the earliest sign that it is promising to consider non-equilibrium systems, to consider periodic driven quantum systems, to generate topological edge states like the integer quantum Hall effect. So indeed, this concept becomes solidified since 2011, because now a number of very prominent studies emerged during this year. within a couple of years after that. For example, we have this now this groundbreaking work published in Nature Physics, how to engineer the band gap or the topological features of the band by periodic driving a quantum well. And in this study, it shows that how to create so-called Majorana edge mode. We are going to say a lot on that later on by driving cold fermion systems. And this is all work. We showed that how to take advantage of the topological features of the gap created to create so-called quantized acceleration. Then experimentally, as a proof of principal experimental relations, this kind of concept was also realized in the photonics waveguide systems or in the surface state of, I believe, three-dimensional topological material. So therefore, because of this earlier pioneering work, the field becomes exploding later on. So now let me qualitatively, as I promised, explain why periodically driven quantum systems suddenly become so interesting. So I think there are three important features we should take note of. First, if we consider a periodic driven quantum system, right? We consider, for example, the propagator from T to T plus capital T is a period of periodic driving. Then, in order to understand the dynamics of the system, all you needed to do is to solve for the eigenvalues of the propagator or Floquet operator of the system. And because this is a unitary, you realize this eigenvalue or the spectrum, or we call it quasi-energy spectrum, is only defined up to 2 pi, because phase is defined only up to 2 pi. And therefore, you automatically create a quasi-energy Brillouin zone. So for example, pi and minus pi are the same, right? And think about it, if you only have 2 bands, and normally for 2-band system, you only have 1 gap. But because of this quasi-energy Brillouin zone, even for 2-band system, you could have 2 gaps. One is around the 0, one is around the pi, because pi and minus pi are the same. And later, because of this, right, eventually you see we can create lots of so-called 0 mode and a pi mode at the edge of the system due to the bulk edge correspondence. And also now you have a time dimension playing a very important role in engineering system. So there will be more symmetry classes of the topological phases, right? We know that it's very important to define what the symmetries we are looking at in order to understand the main qualitative features of the topological gap. The other thing is also very important and cannot be underestimated. Imagine we periodically switch between 2 Hamiltonians, H1 and H2, with each one of a period capital T over 2, and therefore the overall period of the system is T. So the overall time evolution operator can be written as this. You combine those two and equal this to be the overall effective Hamiltonian, right? Now, because H1, H2, okay, are in general not commutable, so you can use so-called BCH formula to write down what's the expression of the effective Hamiltonian. You will realize the effective Hamiltonian equal to the average of the 2 Hamiltonian plus their commutators, plus their commutators and the commutators, and so on and so forth. So therefore, you see, even though H1 and H2 might be relatively simple, by periodically switch between the 2 Hamiltonians, the resulting effective Hamiltonian can be really complicated. For example, if H1, H2 only contain nearest neighbor hopping, then you see this effective Hamiltonian in principle can have next nearest neighbor hopping, next nearest neighbor hopping, and so on and so forth. Or if H1 and H2 only contain 2-body interaction, okay, then by looking at this, H effective contains 3-body interaction, 4-body interaction, and so on and so forth. So I think that's a very important reason why when I apply periodic driving to a quantum systems, there are lots of new features that can be created. So therefore, now this is recognition from the community that now we can apply periodic driving field to a quantum system, which could be otherwise trivial. We can control or we can generate many topological matter. So the main features that I'm going to elaborate on those, of course, we could achieve widely tunable topological invariant. What does that mean? I'm going to highlight this. And we can create extra topological features for novel topological matter. We could also have flexible boundaries to accommodate surface state, because one motivation to create topological states is to make use of the edge state. And now, because of the periodic driving, we can use driving field to create artificial boundaries so that those artificial boundaries can accommodate surface state or topological edge state. And the last but not least, which is highlighted here, is that we can create new opportunities to discover new non-equilibrium physics. Basically, what's the new dynamical aspects of a quantum system that is topologically non-trivial, created by periodic driving. So what about the recent status of this research direction? Well, I'm glad to share that since 2020, there are still lots of experimental activities. So I choose 4 on the screen. For example, this is a paper published in Nature Physics as a letter about light-induced enormous Hall effect. So in this case, people really apply driving field, okay, to actual solid state system graphing to create novel topological features. In this case, is using ultra-cold atoms to realize anomalous Floquet topological systems. In this case, is a photonic quantum walk systems to create chiral edge states. In this case, is nanophotonic lattice systems called realization anomalous Floquet insulators. So those are just 4 out of many in recent 2 years on the experimental activities. So, okay, so one main feature of the non-equilibrium topological matter I'd like to emphasize is that we can create abundant, many edge state in such matter created by periodic driving. So here are some examples. For example, for one-dimensional system plus necessary symmetry, for example, so-called chiral symmetry or particle hole symmetry, we don't have to define what the symmetry it really is, right? The good news is that you can create arbitrary number of topological zero mode and topological pi mode. Zero means the quasi-energy of this edge state is 0, and the pi means the quasi-energy of the edge states are pi. Okay, so here is a sample plot. I'm plotting the profile of this edge state. So you see, for example, the leftmost state is localized at the leftmost them. There are more edge states, so they are localized a little bit more inside the lattice and so on and so forth. So in principle, at one edge, you can create many such topological edge states. And since their energy is all at 0 or pi, that suggests you have opportunities to play with those edge states that are degenerate at the quasi-energy 0 or pi to encode quantum information or to operate on them to do some quantum computation. For 2D systems plus some necessary symmetries, okay, so this is a 2D system, you see, we can create arbitrary number of topological 0 mode and a pi mode at the corner called corner modes. Here are also plotted. At each corner, this 2D lattice accommodate many 0 mode and corner mode at each of this corner. Again, you can think, right? So now probably we can make use of corner mode to do something, maybe to do quantum information transport or to encode quantum information. Another interesting situation for 2D system without any symmetry, okay, even without time reversal symmetry, we show that, for example, in this 2-band system, even though the chain number of each gap is relatively small, in this case, the chain number of upper band and the lower band is +1, -1, but we show you can create arbitrary number of robust edge state. So edge state are plotted here. And those edge state means on the edge of the 2-dimensional systems, okay, those edge can accommodate robust conduction. They become robust conduction channels. And since we could have arbitrary number of such edge state, in principle, we can create arbitrary number of robust conduction channels. So if topological insulator is really important in terms of offering robust conduction channels, I would say this kind of scheme, create many robust conduction channels, is even more important than a normal topological insulator, because this is a topological insulator with many edge state channels. So I hope we can continue to work on those possibilities and can actually find more applications. Now, this is the dynamic days conference. Let me also highlight, right? Even quantum chaos models that early on, where we discovered the butterfly spectrum, it's also quantum chaos model. In 2018, we proposed another quantum chaos model called spin 1/2 double kick rotor model, and under some special quantum resonance conditions, the one period propagator or Floquet operator become this. And you think this sigma x, sigma y are just a simple body matrices, okay? So this is a very simple a model, but look at this. If you look at the phase diagram at the function K1, K2, and those numbers are some winding numbers or topological characterization of the two-band system, you see, okay, you have extremely rich phase diagram for even such a simple system. And if you only look at the x-axis or y-axis, indeed, you confirm that those winding numbers keep increasing without a limit, which means even for such simple systems, you can have unbound number of topological edge modes. And indeed, this kind of quantum chaos models attract interest immediately. So in recent, there are already 2 experimental realizations based on this model to observe new topological phases due to periodical driving. So now come back to our main motivation. Based on all those results so far, what's our dream? How to go forward? So our dream is to make use of topological matter, which offer edge state protected by symmetry and topology, to realize or to observe or to explore non-equilibrium phenomena at a many body or few body level, or to realize robust encoding and processing of quantum information. And we also hope to realize topology protected transport of matter and quantum information. So this sounds a lot. So we are working on those possibilities, and from quite academic point of view, but who knows, maybe at one day, right, the kind of bold ideas we propose could find real world applications. So let me first address this non-equilibrium phenomena due to the novel topological matter. So to do that, let me first recall a now relatively old idea proposed from our group in 2005, and then later on, it was realized, 2015, and later on realized 3 years later in 2018 by Professor Sifaza and Du Jianfeng's group from USTC. So in this case, since we are talking about non-equilibrium systems, we are looking at the superposition of the 2 bands, 2 topological non-trivial band. Then we do adiabatic pumping. And if, okay, we only introduce a mixed state of 2 non-trivial band, then you do topological pumping. Then you realize the charge pumping is just given by the incoherent sum of the charge pumped due to the upper band and the charge pumped due to the second band. Now, think about a non-equilibrium situation to look for more interesting dynamics. In this case, we create an initial state that's a superposition of the upper band and lower band. Then we do adiabatic pumping. In that case, when you do the pumping, you realize the pumping has an extra term here, in addition to the result that can be obtained individually. Well, you might think, oh, well, of course, if you create a superposition, then you could get interference. Well, the situation is much non-trivial than this simple understanding. It turns out that the reason for this is because if you mix a 2-band state, if you do adiabatic pumping, then the interference causes a deviation from adiabatic following at order of 1/t. T is the total time scale of the pumping. This deviation at the order 1 over t looks small, but it can accumulate over a long time scale of adiabatic pumping, eventually causes this. And most surprisingly, this extra contribution actually is proportional to the initial turn-on rate of the pumping. So that is, for example, if your pumping protocol is quadratic, for example, the pumping parameter is 2 pi tau square, which means initial derivative is 0, then there's no such term. But if the pumping protocol is linear with time, initial derivative is now 0, then you see you have this extra contribution due to this effect we predicted in 2015. So this is one example that in topological studies of non-equilibrium systems, you could get new physics, new non-equilibrium phenomena. So this is just a recap of an old study as a motivator. So now let me come to today's focus. Instead of considering superposition of box state, we consider superposition topological edge state. Those edge states are topologically protected. Okay, that means so long as you don't break the symmetry, so long as you maintain periodic driving, yes, even if you change some system parameters, the edge states will be there. Okay, so now imagine, so the zero mode is defined as eigenphase 0, pi mode is defined as eigenphase pi, which so means after one period, the pi edge state would acquire a -1 phase factor. So now, if I consider general initial state, which must be something like a superposition of 0 edge state, pi edge state, then after one period of time evolution, you see this state becomes 0 minus pi. It cannot come back to self, right? So by creating such superposition state, you are already breaking the time translational symmetry of the period t. So therefore, how to recover this initial state? You have to wait for second period capital T to recover the initial state. So overall, the system will display so-called subharmonic response. And this can be termed as boundary time crystal, because even though you drive the quantum system at the period T, the signal of the system display a 2T oscillation. And this kind of time crystal is inherently robust because of the topological protection. So this idea was earlier proposed by us in 2018. And let me come back to the actual model we use. So this actual model, we are going to come back to this model later on. So it's a periodic quench quantum wire or KTF one-dimensional model. And those are the system parameters we are going to see again and again. Okay, so I periodic quench between H1 and H2. Both looks standard. But as I alerted you, if you periodic quench between those two, right, you can create non-trivial topology. And in this case, okay, you can create topological 0 mode, topological pi mode. And therefore, for a general initial state, you see, okay, that the observer of the system will keep oscillating between blue and the red with a period 2t. If you do a Fourier transformation, you'll see the actual frequency is half of the driving frequency of the system. You might think experimentally, how am I going to periodic quench between H1 and H2? Well, don't worry. On actual quantum computer, even for static Hamiltonian, you still have to decompose this into a number of gate operations. So if you want to realize this kind of systems, right, periodic quenched on a quantum computer, you actually don't feel much difference if I propose a static Hamiltonian or I propose a periodic quenched Hamiltonian. So therefore, this kind of possibilities is quite promising for actual studies on future quantum computers. So anyway, experimentally, this kind of subharmonic response protected by topology is at least observed in 3 experimental studies recently. One is from Singapore using acoustic system. So the Hamiltonian, of course, is classical, but the essential physics is the same. The second one is a photonic system. The third one is recently, early on, by a group from China published in Nature. The Hamiltonian is more or less a periodic quenched spin system, which can be translated to Majorana language also. So all the physics are essentially the same. So since I'm involved in this experimental realization of the boundary time crystal, let me use one more slide to illustrate this. So this actual experimental platform looks quite simple, right? So this can be engineered by using 3D printing. Then this is a tight binding model, okay, of this 4-step quench of 4 configurations, okay? So then overall, the system accommodates 0 mode and pi mode at the corner of this 2-dimensional system. And the z-axis is modeled as time dimension. So we inject initial excitation here. Then because of 0 mode and pi mode superposition, right? You see at one period, which is L here, the system's dynamics did not come back to itself. You have to wait to 2t, which in this case is 2L. L is the period of system for the system to come back to itself. So this nicely illustrates that due to the periodic driving, you have created the topological edge mode. And also the superposition of topological 0 mode and pi mode induce a 2t, the subharmonic response or double period oscillation dynamics at the corner of the system. Okay, so now second thing, how are we going to use edge state protected by symmetry and topology to do robust encoding and processing of quantum information? Well, this part is a bit even more technical, but don't worry. We just look at some basic ideas and I will flash some slide. I'm not going to go into the actual details of how exactly we do this kind of thing. But in any case, I have to introduce a little bit about this Majorana 0 mode and Majorana pi mode concept. Okay, so suppose CJ diagram are fermionic creation annihilation operators. Then you can define 2 types of Majorana operators. One is basically real part, one is imaginary part. A is a real part, B is the imaginary part at each lattice site. Then the C is basically a non-local fermion creation operator, annihilation operator. So therefore, C dash C can define occupation number of a non-local fermion. So then we can use 2 such lattices, 2 pairs of such non-local fermion to define 0 means there's no non-local fermion occupied, and 1 means we have non-local fermion occupied on the first lattice and the second lattice. Then, okay, so this is the basics of do Majorana quantum computing. And then if you do a braiding at the 2 edges, what you essentially can achieve is this rotation between qubit 0 and the qubit 1. Okay, so that's the basic idea of how to do information encoding and operation on a single qubit system encoded by 2 pairs of Majoranas. So therefore, let's come back to our 1-dimensional periodic quenched KTF model, which I just used to demonstrate a subharmonic response, right? It turns out that for special parameters, the so-called 0 mode is basically what? The sum of the real part and imaginary part of your Majorana mode. And the pi mode is the difference between the real part and Majorana mode at the first site. But for other system parameters, it's also more or less like this. So from that alone, you can see because 0 mode and pi mode are both important. So therefore, both real part of the fermion creation operator and imaginary part are important. But previously, people only use this to do Majorana quantum computing. Now, this picture shows that both gamma A, gamma B can participate in the information encoding or in the processing of the qubit encoded by Majorana operators. So therefore, or equally speaking, we can now use both 0 mode and a pi mode to do something useful. And therefore, you also realize both pi mode and 0 mode are actually 0 mode of U square, yeah, because pi mode, right? If you solve for the apply pi mode twice, it comes back to itself. So pi mode is also 0 eigenphase of U square. So in that sense, 0 mode and pi mode both form, they are different, but both form degenerate mode of U square operator. And that offers very exciting opportunity to do non-abelian rotation between 0 mode and the pi mode by applying adiabatic control to the quantum system. And this is the phase diagram. You can see if you adjust the system parameters, you see you get a 0 mode and a pi mode depending this regime. Okay, so therefore now we are going to propose, because we want to use both 0 mode and pi mode to do quantum computation. Instead of introduce 2 lattices, we only use 1 lattice. Okay, but now alpha denotes a lattice at even multiple time, and a beta denotes the same lattice at odd multiple of the period. So therefore, we use time to replace space to save, okay, the number of lattices you need. In this, cut 2 into 1, and we are going to do the braiding, okay, at the edge between alpha and beta, quantum-wise. So therefore, you see, indeed, right? We are making use the fact that the system at the time B and the system at the time another period, okay, is not equivalent, and therefore this offers opportunity for us to braid those Majorana mode and to do quantum computation. And then eventually, roughly speaking, what we are going to do, okay, later you are going to periodically change the system parameters along this axis, then you come back to finish one loop to introduce the non-abelian rotation between 0 mode and pi mode. So of course, the detailed operation is here. I'm going to skip. That is for, maybe I should elaborate a little bit on this slide, because later this is relevant to the last part of this presentation. So basically, you hear the blue and the red lines means some interactions you should adapt tune either getting smaller and smaller or increase, okay, gradually. So therefore, you see you can inaccurately solve the expression 0 mode and pi mode. And then if you slowly change phi, you can actually slowly deform 0 mode from being at the first side to at the third side of this system. Okay. Then the second step, you do bring it back, but now the situation changed. The form of 0 mode and pi mode are changed. And the last step, of course, you do something to make sure that you can bring the Hamiltonian back, and eventually you can realize this adiabatic change. And okay, if you are careful enough, you realize our task of braiding between 0 mode and pi mode is not done yet. So if are interested, you can look at the details. You realize we have to repeat the whole process again. Eventually, we realize this braiding operations. And those are some results. You can see, you can check the correlation between the Majorana mode to make sure actually we do exactly the required or planned braiding operation between the braiding operation of 0 mode and the pi mode. The nice thing about this is that when I do 0 mode and pi mode, you see, right? 0 mode and pi mode are always well separated from the gap. So therefore, right, this kind of operation is protected by the gap from the topological edge state to the box state. So now, how to scale up this idea? Well, we can introduce sub-lattice degree of freedom to the lattice. Then we periodic quench between H1, H2. In this case, okay, you solve for some details. You realize indeed now at one edge you could have 2 0 mode and 1 pi mode. On the other edge, of course, you have also 2 mode, 0 mode and 1 pi mode. So that means now we have more possibility to encoding. We can encode 2 qubits on one edge already. So we define parity of operators, and we define this 0, 0, 0 means, okay, 0 parity for the 3 operators, and call 0, 0 as the 0, 0 for the encoded qubit. Then define other qubit state for the encoded 2 qubit or 4-dimensional subspace. And then similarly, okay, by looking at some details of Hamiltonian, you can find that you can tune some system parameters to realize the braiding between the 2 0 mode and to realize the braiding between 0 mode and the pi mode. So therefore, essentially, you can do gate operations in the 2 qubit subspace at one end of this lattice. We even propose how to use this kind of braiding between 0 mode and pi mode to realize a simple inversion algorithm. We call this as Floquet quantum computation because it's entirely relied on the edge mode in Floquet system protected by Floquet topological band. So this is the for example, if you want to invert 0, 0, 0, 1, 1, 0, 1, 1, you are going to do this kind of operation, braiding operations. Now, early on, I mentioned, right, the one advantage of this Floquet topological states is that you can create arbitrary number edge mode. So in this case, for example, if we want to create 14 Majorana mode on both edges or 7 Majorana mode at one edge, well, you look at the phase diagram, you realize, oh, if I tune some system parameters at this regime, okay, you can count them from the topological invariant. You can realize, oh, in this case, that means you have 4, okay, 0 mode and 3 pi mode. And totally you have 14 Majorana mode. So then you can use 14 Majorana mode on a single quantum wire, okay, to do a quantum error correction code. In this case, right, all the possible errors listed here, and those errors can be what? Because those error operators can be stabilized or anti-commute with all those operations. So in principle, yeah, we know what we should do if we want to use multiple Majorana mode to implement this kind of a simple error correction code. What about 2D Floquet topological matter? Well, you can follow the same idea. So you couple many wires together, and by engineering those couplings between one device in a non-trivial fashion, you can inspect the phase diagram. Then you can see, you can realize the Majorana 0 mode, Majorana pi mode, and the regime of coexistence, okay, at the corner to realize 0 mode and pi mode. And we realize back in 2020, we can make use of 0 mode pi mode at the corner to do so-called measurement-based quantum computing. So this is a simple idea. First, now you have 1 pair, 2nd pair, 3rd pair, 4th pair. You have 4 pairs of 0 mode and a pi mode. Then, for example, we can use those Majorana operators at different corners to encode, in this case, 3 qubits. Okay, so the corresponding operators is like this. Once you realize this encoding, then you can think about how to realize gate operations by measuring, yeah, this code, the qubits encoded this way. In terms of that, okay, you can you can play with the flux between the lead and the system like this, and you make use of interference. For example, the system can, the Majorana particle can absorb here and reappear here because those are non-local Majorana particle, right? Or the conducts can go from here, come from here, and the system can also come from here and here, then here. So by playing with those interference, okay, and measuring the conductance, in principle, you can measure all the expectation value of these operators. Then based on what you get, you decide what you do in next step. And then therefore you can realize those kind of gate operations in the encoded system. For example, in this case, to realize the C not gate, you have to do this kind of measurement in sequence. Okay, so towards the, I'm almost at the end. So now, how to do topological predict transport of quantum information? Well, actually, you see something like this already. So, for example, we propose a situation. Suppose this is a system can accommodate 0 mode and a pi mode, and we want to transfer this input from here to here. And we realize entangled state of a spin chain can be expressed as a superposition of 0 mode and a pi mode. And yeah, during the middle of my talk, I showed that you can adiabatically change the system parameter to move 0 mode and pi mode along the lattice. And the 0 mode, pi mode, right, are good in this case because you don't have to worry about the dynamical phases during the time evolution. Because 0 mode has 0 dynamical phase, pi mode has 0 dynamic phase after each 2 period. So therefore, by moving 0 mode and pi mode and the superposition adiabatically along the lattice, you can move entangled state along the lattice. So we indeed, this is some technical details. For example, by focusing on the first two sides, okay, you realize zero mode is this expression, pi mode is this expression. So by adiabatic change the system parameter phi, you essentially can move zero mode from here to here and pi mode from here to here. And therefore, any superposition like this can be moved. Therefore, you can transport entangled state along this chain. And this is the before this adiabatic protocol. This is at the end of adiabatic protocol. Okay, so before I conclude, let me also share with you two latest experiments I'm involved with. One is observation of the Floquet topological phases with large chain numbers. So I think now one key issue is, we know we can use periodic driving to create topological phases with big chain numbers. But in experiments, how I'm going to characterize, how I'm going to confirm you have realized those topological phases, right? So in this experiment, we show that by measuring the spin texture of the systems, this is the simulation result, this experimental result, you can connect the spin texture winding behavior to large chain numbers of the topological phase. In the second experiment is so-called more exotic phases in non-equilibrium topological matter, so-called pi over 2 modes. So this is a tighter binding model of periodic quench system. Okay, the initial configuration like this, then the second configuration, and then third one, and so on. So by playing with this, you realize you actually the system can not only have zero mode and pi mode at edge, you could also have so-called pi over 2 mode at the edge. So for general initial state, since you evolve zero mode, pi over 2 mode, you can imagine the response of the system, okay, is not just at the period of 2t. Actually, the response is actually at the period of 4t. T is the driving period of the system. So this is a simulation result. This is the actual experimental result. So due to a lot of noise, the experimental result, right, even though showed the signature of 4t oscillation, is still, you can see there are some noise in the experimental system. Nevertheless, in this acoustic system, we also show that it is possible to observe more exotic phases. And we anticipate when you translate this idea into many body quantum systems, right, you could anticipate more applications in using this kind of exotic mode, exotic edge mode to do encoding, to do quantum information transfer. Okay, so let me conclude. Floquet topological phases are extremely rich, offering many possibilities in encoding quantum information or transporting quantum information. And especially I highlight the so-called Majorana pi mode, Majorana zero mode. They allow for scalable quantum computation protocols, and those protocols are protected by symmetry and topology. And we propose two specific schemes. One is adiabatic quantum computation scheme, one is measurement-based quantum computation scheme. So I also hope I have made it clear that topological boundary states can lead to many exotic non-equilibrium phenomena and can be already accessed by various experimental platforms. Thank you very much. I end here.
Thank you very much for the interesting talk. Are there any questions?
Hello, thank you for your nice talk. So I was just wondering that when you mentioned that there is a arbitrary number of edge state.
Yes.
How arbitrary this number is experimentally or practically?
Yeah, certainly. Okay, this is a very relevant question. In theory, right? Okay, there's no limit so long as you can arbitrarily tune the system parameters, right? But of course, in experiments, there's always limitations. So I think eventually, what's experimental limitation depends on what the platform we are considering. Yeah, but I'm optimistic in experiment we could eventually push up to tens. Okay, above 10. Right now, in the latest experiment, for example, chain number is equal to 4 in experiment by USTC. But you can easily polish the experiment and push a little bit more. I think there's no. the winding number as high as 10 or the chain number as high as 10.
Okay, thank you. Yeah.
Thank you.
Thank you for the nice talk. I was wondering if I understood correctly, most of the results were essentially for the non-interacting case of systems, and you emphasized that there could be many, many body applications. So I was wondering if you could comment on what the main obstacles are to transfer these results to the many body setting, in particular because Floquet systems with interactions are in some cases not very conducive to having long-lived, nice states that are controllable.
Wow, yes, great question. Yes, of course, yes, indeed. At the conceptual level, many of the physics I just shared with you is on based single particle. There's no interaction. When you turn on interaction, apparently there's new physics coming in because, for example, the heating issue, right? Are you in this pre-thermal phase and so on and so forth. And eventually we hope experimental people can realize Floquet topological phases in the pre-thermal plateau, yeah, in interacting systems. But on the other hand, right, this kind of Majorana modes and so on, they are already in the many-body interacting system in the spin systems, right? For example, even in this experimental systems I mentioned, 1 second. In this experimental system, in the digital quantum simulation for located symmetry project topological phases, right? Look at system, it's apparently a many-body system, but yet, right, this many-body system can be still well understood in the Majorana language. So therefore, somehow the single particle physics can also be relevant in this kind of engineered many-body spin system.
I think that we are running out of time, so let's thank the speaker again.
Thank you all very much.